All right, I want to start off today with an announcement. I told you last week, I don't know, did I tell you that we had a faculty member pass away? Okay, so I was asked to take over her class, so one of her classes. So I took over her pre-cal class, which is Monday, Wednesday, 9 a.m. to 10:40, and so that's usually what I've been in my office before this class. So I'm just letting you know that my office hours are no longer Monday, Wednesday, 9 to 11 anymore. Okay? As far as adding new office hours, I have to figure out where it would work in my schedule. I don't really have any more time slots available for office hours. Now I do have them on Tuesday, Thursday, but on Monday, Wednesday, I'm pretty much teaching from 9 till 3 straight through, no break. I mean, break to get from one class to the next, but so by the time I get back to my office at 3, I'll probably just be there for an hour, and I got to eat and everything else. So, um, but let's just see how things go. So that's the first thing. Next thing, the take-home quiz. Everyone's turned that in. Any questions on this? Any issues? A lot of algebra in there, yeah. I don't have the new one for you. It's going to take me probably a couple of days to get caught up on things because I'm having to basically prep an entire course that I wasn't ready to prep. I haven't taught pre-cal in years, so I've got to create their Canvas page and all that stuff, get everything set up. Yeah, well, yeah. Any time I haven't taught it in a long time, we have a new textbook. If we were using the same textbook that I used a couple of years ago, I'd do that. But there's just a lot of work to prep for it. So you probably won't get um, your next take home until after our midterm. Our midterm is coming up, isn't it? Is it a week, 2 weeks from today, or a week from today? A week from today. Ooh, yes, a week from today. That's, whew, all right, well, yeah. All right, so let's get through Chapter 11, Section 7, which is where we ended last time. And we had been talking about finding the maximum and minimum values of a function of two variables when our domain was not restricted, right? So we would say just on its implied domain, where does the graph have its highest and lowest points? So today we're going to look at finding what we call the absolute maximum and minimum values, or minimums, on a closed bounded set. And we already talked about this, but I'll remind you because it was a long weekend. Back in Cal 1, if you have a function on a closed bounded set, so the domain has now been restricted on this interval AB, right? So I could look at that. The notation here is our domain would be all the numbers in between A and B, including A and B, right? So this is why we call this a closed set, right? This would be the domain. X is an element of that closed set right there. Our function is defined on that closed set. Then what we learned in Cal 1 was that if it's on a closed set, you have not just local maxes and mins, you should have a global maximum and a global minimum, or another word for that is an absolute maximum or an absolute minimum. So a highest value the graph ever takes on, and a lowest it ever takes on that domain. In this particular problem, I don't like my drawing. Let me do it a little different. Do it like that instead. On this particular problem, the absolute maximum actually occurs at an endpoint, right? At the endpoint B is where we have the highest point on the entire graph. But our absolute minimum occurs at some point in here, which I'll call C. And that C is where we have a critical value, or a critical number. That's where the derivative is 0, right? Right. Okay. So what we're going to be doing is, by looking at these surfaces on a domain now, on a restricted domain, we're going to have to look on the inside, just like we did here. And how did in Cal 1, to look on the inside, we did like first and second derivative test, right? So in our surface, to find out what's happening on the inside, we're going to use that computation of D, capital D, right? Which was the partial, remember the formula for it? I had it written down over there. What is it? We'll use it again today, so let's see if we've... D of xy was partial xx fyy there you go. Okay, that's how we computed D. And then we had all these different results, saddle point, local max, local min. So when we're going to restrict our surface to a closed region, a closed set, we will still have to look on the inside, and that will require the computation of D. But then we have to look on the boundaries also. Just like over here, we had to look at the endpoints and compare that to this, to these, to the inside. And that's going to be the biggest challenge, is how do you actually look at a boundary or endpoints if your domain is two-dimensional instead of here where it's one-dimensional. All right, so we first have to get some the idea down of what a closed bounded set is. Here are some pictures. Remember, in a function of two variables, our domain is on the ground, right? So it's flat. It's like a two-dimensional region. If that region looks like this or like this, we call it a closed bounded set. Closed meaning that we include the boundary. All the points on the edges are included. That's what makes it a closed set. And then bounded set, what makes it bounded? Well, here's an example. Let's say we take in two-dimensional space. I take everything here to the right forever. All right? That set is not bounded. It's unbounded. It just keeps going forever. So not only do you have to include the edges, you can't go forever in any particular direction. So this would not be a closed bounded set. Here's another way of looking at it. Closed set in R2 is one that contains all of its boundary points. A bounded set is one that is contained within some disk. So if it's a bounded set, there's some way to draw a disk around it, and it's all inside that disk. All right, the extreme value theorem for functions of two variables. This is kind of like, what's the approach we're going to use, all right, to try and find the absolute max and min? To find them, we find the value of f at the critical points of f and d. Now don't confuse this d here with that d. That d is what we computed to try and find, these local max and mins. This d is referring to the domain. So we find the critical points. What are the critical points? It's where the first partials are 0. Right? Isn't that what we did to compute d over there? What was the first thing we did? We found out where the first partials were equal to 0. And then we computed d after that. We still need to do that. But instead of having to compute d, you'll see what we do. All we do is just figure out what these points are, and then we just keep them and hold on to them for a second. And then we find the extreme values of f on the boundary. So we're going to move around the boundary and figure out what f is doing. That's going to be difficult. And then what we do is we compare the two answers here, and the largest is going to be our absolute max, and the smallest is our min. That's the technique. Let's just do an example, and then you'll see how it works, okay? But the big picture of what I want you to realize is happening is the first thing we're going to do is look inside the closed bounded set, figure out where its highest and lowest points can occur, and then we're going to look on the boundary, and then after that, compare them all. So here is the first example. Find the absolute maximum minimum values of this function on this closed triangle with these vertices. Now, I did show you this at the end of class last time, right? We have a triangle, two-dimensional space. We map that triangle up into the surface. Y'all remember this picture? And we had this green-looking thing here. It's obvious that we have what looks to be like some low points and some high points, right? And if I look at it from the top, would you agree that 3 of the points occurred at the vertices of the triangle? Yes? But this 4th point occurred on the boundary of the triangle, right? But not at the vertice. It's somewhere in here. So how are we going to find these, all right? All right, so I have it all worked out here, but I'm going to go ahead and go through this. So first thing I'm going to do, write down the function 3 plus x y minus x minus 2y. I'm going to go ahead and draw a picture of our situation. I have the x and y axes. I have my triangle with vertices 1, 0. Five, 0. And 1, 4. All right, there's my domain. We call that D over here. Again, let's not confuse it with that D. So if I want to know what's happening on the inside of this, that's basically saying, let's act like we haven't restricted the surface to that triangle. Let's just look to see where we have high and low points. Where do they occur? So to do that, we'll need the first partial first, and we'll set it to 0. So where's the first partial here? Or what is the first partial here? Y minus 1, right? The other partial, x minus 2. Now set each of these equal to 0. When is the first partial with respect to x equal to 0? When y is 1? When is the first partial with respect to y equals 0? When x is 2. Therefore, the point 2, 1, right? 2, 1 is what we call a critical point. It could be that this point represents a highest or lowest point on our graph, right? Now, what we did before, and this is where we have to make the distinction between what we did previous class and today, is when we had that critical point, we then went and computed D. We don't have to do that step anymore. Right? What we need to do is just make sure we get the critical point, and we will now plug that critical point into the function and figure out what its value is. The analogy is this. I can sit here and find this point, right? By taking the first derivative and finding when it's set equal to 0. And then all I have to do is plug that point into the function and figure out how high this is, right? Once I know how high this one is, and I know what the two endpoints are, I compare all of them. The highest is the highest, the lowest is the lowest. So I don't need to know if this was a local max or a local min. That doesn't matter, because I'm just plug it in and figure out what the value is. Understand? Okay. So let's go ahead and plug that in. What is f of 2, 1? So what do we got there? 5. Is our brain working? 5? 1? What do what is it? 5 minus 2, right? Minus 2, which is 1. So we should get, yes? All right, it's Monday. Now I'm putting it as an ordered triple. This is a point, right? That's a point on my surface, an x, y, and z coordinate for this point. What's most important to me is that z coordinate, because that tells me how high I am, right? I am 1 unit up. And I'll compare that to what's happening on the edges. Any questions? That's pretty much going to be the easiest part of the problem, is that right there. Well, what we did last time is we had to figure out what the point was, right? And we had to figure out, is it a local max, a local min, or a saddle point, right? We had to actually figure out what it was. Here, we don't have to, because all we're going to do is look at the z value and compare it to everything that's happening on the boundary. Like, let's say we go around the boundary of this thing, the triangle, and let's say that we're able to determine that along the triangle, it never gets bigger than 0. Then this has got to be the highest point, right? Yes? Let's see here. Remember, this is the surface, right? Right here. And bring it back in here and bring the surface back. Okay, there's the surface, right? We're looking at that green thing inside. Now, we don't know this, okay, because just algebraically, without the picture, we don't realize this. But what we found is actually, that 0.12 is actually a what? Can you tell from the picture? It's a saddle point. But I don't care anymore because I'm looking just on this triangle. I'm not trying to figure out where the saddle point is or where the local min or local max is. I'm trying to figure out the highest and lowest points on this little triangle piece. It could turn out that it's at one of the local maxes or local mins. It could turn out that way, but in this case, it's not. It's just too much work for us in general to go calculate D to figure out if it's a max or min. It's just more extra effort that we don't have to actually exert. Okay, so now that I've done that, I need to now figure out the function's value along the triangle. Now this triangle, it's too much to look at all of the triangle at one time. So what we do is we break the triangle down into pieces. And we break it down into what seems natural here, 3 different pieces, right? The 3 edges. And let me stick with what my notes are. L1. Okay. So I'm going to label this. I'm going to label this right here L1. This right here L2. And this right here L3. So I've broken it down into 3 lines, haven't I? And what I want to figure out is what happens if I take just points on this first line, just the points on L1, and plug those up into the function. Right? Just those points on line into the function. What would that give you up there? What would it look like? Would it be a surface? Would it be, it'd just be a curved line, wouldn't it? It would just be a line up there? Now, I've done it so you can see it here. Let me pull this out. Pull the points out. So look, L1 is this edge, right? If you take that edge and you map it up into the surface, there's L1 on the ground. Okay, there's L1 on the ground. But then when you take like this corner point and put it into the function, it comes up here, right? Then you take this point, it goes up. Then they're getting smaller and smaller. At this point, it looks like it's 0. And then it goes below the XY plane. It's below the ground. Do y'all see that? So it looks like that line, when I plug it in to the surface, it gets mapped to a line, doesn't it? And since it's a line, I should be able to find the max and min of a line, shouldn't I? If I have a line, draw it on a closed interval, I should be able to tell you what the highest and lowest points are. But we have to be able to do this algebraically, again, without the picture. So on L1, let's talk about what's happening on L1. On L1, every point on L1 has the same format, doesn't it? since they lie on the x-axis, the y-coordinate is always 0. Agreed? So I could say the y is always 0. The x, well, the x is whatever x is, right? It takes on some x value here. But I know that the x value must be restricted between where and where? 1 and 5, right? So I'm going to put here 1 less than or equal to x less than or equal to 5. So that's the domain restriction of L1. It's saying just points on that line. Now let's figure out what happens when I take points that look like that and plug them into the function. So let's plug points that look like x0 into the function. And so go in here and replace x's with x's and y's with zeros. And what are you left with? 3 minus x. Everyone okay with that? Now, act like you're in Calculus 1, all right? Although you really wouldn't even have to do that. What you have here is a function of one variable, don't you? I changed colors there. I'm just going to call it h. You have a function of one variable, right? The function is 3x, 3 minus x. You're looking at it on this closed interval 1, 5. How do we find the maximum and minimum value, the absolute max and min value of a function of one variable on a closed interval? Well, we take the derivative, right? Set it equal to 0. What's the derivative of this? Just -1, right? Derivative of that's -1, but when is that derivative 0? Never, right? So we don't have any critical numbers here, right? We don't have any critical numbers. So if you don't find critical numbers, then where's your absolute max and min have to be then? At the endpoints, right? So now all I have to do is evaluate this function h at the 2 endpoints. What do I get if I plug 1 into this little h function here? I get 2, and when I plug in 5, I get -2. Follow it? So if I replace the x in here with 1, this thing spits out 2. That's going to be my max, right? This is my max. And then this one will be my min. So let's go back now to this, and let's write down the results here. We already know I'm plugging in a point that has to look like this, has to have a y-coordinate of 0. And we just determined that if you replace the x with 1, this should spit out a 2, right? So I just replace this 1 here. That gives me 2. And if I replace it with 5, it gives me -2. And I'm just going to box this up, and I'm going to come back to it, because I'm not done, right? All I've done is figured out what's happening to my surface along that L1. I know that along L1, I have a highest point of 2 and a lowest point of -2, and I know where they occur, right? You could even write these as, if you wanted to, as ordered triples. This would be the point 1, 0, 2, and this one would be 5, 0, -2. Are y'all following this? I mean, we're moving along that line? Okay. So now we need to move along the next line. The next line is L2, right? L2. So I'll do that one next to this. On L2, all our points look like what? It's not as straightforward as the other one. We need to look at this line. Pick some arbitrary point here. Tell me what its x and y coordinates are. Well, the x coordinate is some x, right? We don't know what it is. But the y coordinate is not 0 like it was on L1. The y coordinate is somehow a function of x. How are you going to determine what it is? slope of a line. You actually need to come up with the equation of that line, don't you? What is the equation of this line? Y equals minus x plus 5. Everyone agree? What's the y-intercept of this line? 1, 2, 3, 4. It would intercept at 5, wouldn't it? So the y-intercept is 5, and the slope is -1. Is it -1? See, it goes down 4 over 4, doesn't it? So it is -1. But in the big picture of things, you know 2 points, don't you? If you have 2 points, you should be able to come up with the equation of a line. So if you were given enough time, you would be able to determine that the equation of this line is y equals -x plus 5. And because of that, you know that this y-coordinate must always be -x plus 5. And now, once we know that, we come down here and say, okay, on L2, all our points look like x, -x plus 5. And what are we going to do with those, with this now? Plug it into the function and see what happens, right? So what does the function do with this? Well, f of x, -x plus 5, turns out to be 3 plus, I lost my function, 3 plus x times y minus x minus 2 times y, but the y is -x plus 5. So we have to do some distribution and stuff through here, right, and clean this up. You should get -x squared plus 6x. I'm going off my notes, so I don't know. Is that right? Yes? Now, when you look at this, what we're saying is, when we moved along L1, right, and plugged it in, the image of L1 was a line, right? It was a line. This one was, we move along L2, which is, again, a line, right? The image of it up into the surface is what? A parabola. It's a parabola. And parabolas, and this parabola in particular opens which way? Down. So it should look like a parabola opening down. Now, if we go here, let me take L1 out of there. L2 L2 is this right here, right? So when I map it into the graph, it should be up over here. So here's L2. See it on the ground? On the ground, it's this. But when you get mapped up into it, it goes like that. So that obviously has a highest point, doesn't it? Now, we have to be able to find that. So let me go back to this. Again, my function restricted to L2 turns out to be a function of a single variable. So I go back to Cal 1. I'll call it H again. I have this parabola. It's restricted on what domain? What's my domain restriction here? 1 to 5 again, right? Because x is restricted between 1 and 5. So I take my derivative as I did before. This time my derivative is non-trivial. It's -2x plus 6. Now I set that derivative equal to 0, and I get x must be 3. Yes? So that's like a mini critical point now. After we figure out where the derivative is 0 and where it's undefined, but we haven't run into that yet. After we find the critical points, we now compare what's happening here to what's happening at these two endpoints, right? So I need to do a comparison. In the previous problem, we didn't have to worry about that, right? Because it was never 0. So now, taking h, let me evaluate h at the critical point. Let me take h at the endpoint. h of 1, then h of 5. So what do you get when you plug 3 into this function h right here? You should get 2. What happens if you plug in 1? You should get negative 2. And if you plug in 5, you should get negative 2 again. It looks like we have a max happening here, and the min is the same, right? At 2 different places. We have 2 mins. Do y'all see that? So what I'd like to do now is convert this back over so I can kind of see what those points are. We were plugging in 3 here for what variable? X, right? So that X was our 3. So up here, if this is 3, then what's this? 2, right? And it spits out what? 2. So if I plug in 3, the y coordinate has to be 2, and then the function's value there is 2. If I plug in 1 for x, I have a 1 here, and then what do I have in the y coordinate? If x is 1, y is 4, and what's the value there? Negative 2. And if I plug in 5 for x, I get what for y? That's what I get for z. I get 0 for y, and then negative 2 for z. Just want to make sure you understand, these are the x values. The y values are coming from this little condition, and then the actual function values are just these 3 numbers. So as points, these are the points 3, 2, 1, 4, negative 2, and 5, 0, negative 2. What I'm doing is I'm building a list of numbers, right? And at the very end, I'm going to compare all of them, and I'm looking for the one that has the biggest z-coordinate and the smallest z-coordinate. And there's no other way to go around the edge than what I'm doing. I mean, this is it. This is the best method. So the last one is L3, right? I have to go to a new page for L3. Yep. On L3, what do all the points on L3 look like? X is always 1. And the y coordinate, it goes from 0 to 4, but it's just y, right? It's whatever the y value is. But I'm going to restrict that y between 0 and 4. And now let's plug points that look like that into the function. If you do that without showing it, it's just 2 minus y. That's what will happen. Again, I'm going to convert this to a Cal 1 problem. I'm going to call it h of y instead of x is 2 minus y. What's the derivative of this? Negative 1. That means the derivative is never 0, right? So I don't have to worry about that. Also, what was my restriction on my y? It was between 0 and 4. I should put that here. Right? I was restricting it. The derivative was never 0. So now I just plug in the endpoints 0 and 4 into this. So h of 0 gave me 2. H of 4 gave me negative 2. Questions? Now, as a function for those 2 points, I was replacing what variable with 0 and what variable with 4 here? The y, right? So the y coordinate is the one that gets the 0, then the y coordinate is the one that gets the 4, and then what about the x coordinate? It's always 1, right? So this is going to be 1, 0, and what should the function spit out there? 2, and at 1, 4, it should spit out -2. So written as points, 1, 0, 2, 1, 4, -2. A lot of these are repeated, aren't they? Don't we have the same points occurring in some of these sets? Y'all notice that? So it looks like the maximum value of the function on the closed set, the maximum it ever gets is what? 2. The maximum value is 2, but it occurs at different places, doesn't it? It occurs, let's see, we have to go back to the beginning of the problem. Remember this one, right? Don't forget this one. Is that going to be part of our answer? Is this a maximum? No, 1 is, there was a point out there that was bigger than 1, right? Was there a point smaller than 1? Yeah, -2. So even though we got something there, do you see it's not going to contribute to our answer? But it could. So don't forget to go back and look at that one. So that's definitely not in our candidate there. Let's see, our maxes are occurring here. There's another one here. Is that the same one from earlier? Yes? Right, so we have a max. We have a max at the point 1, 0, 2, and also at 3, 2, 2. And then where do we have a min? 1, 4, -2, and the other point was 5, 0, -2. That's it. This is what I would want on the test or on the take-home quiz. And I like the answers written as ordered triples because with the ordered triple, you know everything, right? You know how many of them there were. There are 2 places where I have a minimum. The minimum value is -2. I have 2 places where I have a maximum, and the maximum value is 2. And that matches up with the picture we had, right? Looks like we have 2 points where we have a max and 2 points where we have mins. A lot of work, right? It's more tedious than anything else. There's not a whole lot of like crazy algebra or anything we have to do. Derivatives aren't too messy, but it's a process. No, because you'll be asked to find the absolute max and min. That's it. You won't be asked to find saddle points. So it's a good question because look at the difference between the instructions on something like this. Find the absolute max and min of a function, and then they give you some domain restriction. As opposed to this, where it just says find local max, local min, and saddles. Here you're not restricted, so you have to find D for each of those. All right. Here's another one. Different function. This time we're restricted onto a rectangle. So there's my rectangle in 2-dimensional space. There's my rectangle in 3-dimensional space. Here's the surface. Here's the surface restricted to the domain. So I'm pull the surface out, and you can see that it creates this, kind of folded up piece of paper almost, right? We're trying to find the max and mins of this. Absolute max and mins. You can tell from the picture we should have 1 absolute max and 2 absolute mins, right? 2 places where it occurs, it looks like. So if we're going to do this, to get the inside, we just need to look at where the first partials are equal to 0. To go around the outside, we're going to have to do what? Maybe L1, L2, L3, L4, right? Uh-oh. I haven't heard that one in a while. All right, so let me try and just work through the notes and see if, without me having to write this all down. So to figure out what's happening on the inside, I'm going to take the first partials, right? So here are the first partials. I set them both equal to 0. Well, actually, I solved this one. This one gives me an x value of 1. Once I know what x is, I can come over here and figure out what y is. All right? So you solve that, and you get x is 1, y is 1. If we plug that in, we get the point 1, 1, 1. Also, notice 1, 1, 1, 1 is inside of our surface, isn't it? Our domain? It's in there. What if the critical point would have been negative 1, 1? We ignore it. That's super important here because you're restricted. When you do this first partial is equal to 0, it doesn't know you're restricted. So the answer or answers may come up to be points that are not in your domain restriction. So if it's not, you chunk it. Yes. Remember, all these notes are online too, so you can print these off. Yeah, that's fine. Okay, so we have that point. We come back to it. Now we have L1, L2, L3, L4. So I labeled this one L1. So on L1, all the points have to look like what? Ordered pair. 0 for y, x is just x, right? But x has to be between 1 and 3. So on L1, all our points look like x0, where x is between 0 and 3. If we plug x0 into the function, we get, after we simplify it, we get just x squared, which is a parabola. Now we just need the max min of that. So I do mine a little bit different notation-wise, but I take its derivative, right? The derivative of x squared is 2x. I set that equal to 0, and I get what? 0 for x. Now you have to plug in the 0 we just found and 3 into the function. Now, why am I only doing 0 and 3? Yeah, the critical point actually turned out to be the endpoint also, right? So I have to do the two endpoints, 0 and 3, but my critical point, setting the derivative 0, was also 0, so it gave me the same value. So I plug in two different ones, 0 and 3, and I get these results. Is it okay for me to work it through this like this, or do you want me to write it all out? You all okay with this? Are you sure? Okay, so we have two potential places, right? 0, 0, 0, 3, 0, 9. Now in L2, all those points were this. So your x-coordinate is stuck, right? Your x-coordinate is stuck at 3, and your y-coordinate is between 0 and 2. You plug those into the function, you see what happens. Now, when you do your own problems, you could call this L1, L2, L3, L4, it doesn't matter. But on a test, I need to see it, though. I need to see, label it, draw it. That way I can follow your work. So when I go on L2, plugging in 3y, our y is between 0 and 2. We go through it, and we get a line to come out. So I don't even, well, do I do the derivative? Yeah, I do. Say, all right, well, derivative is -4. That's no solution here. Just plugging in the endpoints, we go ahead and we get these two solutions here. Then you go along L3, same thing. L4, I'm not going to go through these. And then at the very end, you look at them all, you compare them, and you determine that the smallest value you ever got was 0 coming out, and it happened at 2 places. The biggest value you got was 9 to come out, and it happened at 1 place. And we're done. Another surface. Now look at this domain restriction. Your D is the set of points where your x is negative I'm sorry, your x is positive, right? X is greater than or equal to 0. Your y is greater than or equal to 0. So that means you're in the first quadrant, and you can include the axes. And then x squared plus y squared is less than or equal to 3. X squared plus y squared equals 3 would be a circle, right? With a radius of square root of 3, right? And this is everything including that and everything smaller. So the domain of this is this quarter circle, isn't it? Quarter circle. All x is bigger than 0, y is bigger than 0, and x's and y's must be smaller than or equal to a circle radius root 3. So if I'm going to be plugging just that into this surface, here's my surface over here, right? If I plug just those in, I get this pretty cool looking shape over here. And you can tell it's the first time this has happened. I think it's the first time this happened, where our highest point is actually not occurring at one of those corner points. It's occurring somewhere on the arc of this circle is where we get the highest point on the function. Okay, so let's go through this. First thing you would do, take your partials, set them equal to 0. If you do this, set that one to 0, you get y is 0. And once y is 0, it tells you x has to be 0. Right? So buy that or no? Or what does this say here? Look, what's the only way this equation can be true? If y is 0, right? Now, if y is 0, isn't this one always true also? Regardless of what x is? Regardless. Which means that you could take any point that has the form any x value and y is 0, and you would satisfy these two, wouldn't you? What I'm trying to explain is that any point x0, which would be along this edge, actually is a critical point of the function. Do you remember that bonus question I gave you all? I said you can mess with it, and that I don't think I've ever had a student figure out this one little issue with it. This is very much related to that. Because usually when we did this, set these partials equal to 0, we usually got like a single point, right? This is telling us that we're actually getting an entire line segment where it happens. So we have to actually figure out what's happening along this edge. But that's okay because we already are going to do that, right? We're going to call this maybe L1. Yeah, call this L1. We'll call this part L2 and this one L3. Now, we've used L for line, haven't we? L1. Do you agree that going along that arc, it's no longer a line? But is it okay? We still call it L2? We're all okay with that? So on L1, all your points look like this. Your x is between here and here. You're comfortable with the root 3? Radius of the circle? Okay. Then you go through that process again, and you get this. Your x can be whatever it wants, 0, 0. All right, so that might be a minimum or a max. Now, L2 is the one that's interesting, I think. Because if you're on L2, if you're on this, the x-coordinate is whatever the x-coordinate is. How is it that I'm getting this y-coordinate right here? Where's that coming from? Yeah, when you're on that circle, your points here come from this equation. So if you solve for y, right, that's what you get. And we only have to take the positive case because we're in the first quadrant. So that's where that comes from. That's where this is. And now you plug it into the function, and when you do that, you get a cubic function. Right? That's a cubic. Now you're trying to find the maximum and minimum values of a cubic function on this interval. So you have to take its derivative. You take its derivative and you get this quadratic. Once you take derivative, you have to set it equal to 0, right? So you set the quadratic equal to 0, find the two solutions, 1 and negative 1. But 1 is the only solution. Why? Because negative 1 is not in our domain, right? Like back up here, negative 1's over here. You're not allowed to be there, so you throw the negative 1 out. And now plugging 1 in and plugging in the two endpoints, you get these 3 points. Potentially a local max, potentially the maximum is here, right? Because the z value is 2. But then you have to move along L3. When you go through L3, it's pretty clean. You get this. You compare everything, and you get some interesting results. The minimum value of this function is 0. That's the smallest it ever is. The biggest it ever is 2. It only achieves the value of 2 at one single point. But the value of 0, the minimum, actually occurs along both of the boundaries L1 and L3. So along that entire edge, it's always 0. So you don't have a single absolute minimum point. You have one minimum value, 0, but it happens at infinitely many points along those edges. I hope you could see that from this picture. I only have the points listed at the corners, but it's along this edge right here and this edge right here that the function is 0. Yeah. This surface comes down and just, it's like someone taped the edges of the function down to the ground there. But it's pulled up in the back. Can you see that? Can you see that from the side? Okay. All right, so let's see how we could use this in an application. Find the volume of the largest rectangular box with edges parallel to the axis that can be inscribed in the ellipsoid 9x squared plus 36y squared plus 4z squared equals 36. So you have this ellipsoid, right? You got this ellipsoid, like an egg. Been given the equation of it right here. And we want to come in here and put a box inside of it. This box needs to be a rectangular box, which we call a parallel pipette. It's a rectangular box. We want to put one in here where the edges of the box touch the ellipsoid, right? It touches here, touches here, touches, right? All the corners touch. And we want to know what the dimensions of that box need to be to get the greatest volume possible. All right? The greatest volume. So the way that we are going to approach it is by not looking at the entire box, but looking at just one section of it. And I know this projector really sucks, but let me see if I can't get this to be a little bigger here. Well, that didn't work. Doesn't want me to do that. Try it one more time. No, it doesn't like me. We'll do this instead. All right, do you remember when we first talked about three-dimensional space, we talked about octants, first octant, second octant, third octant? This green box is just a box in the first octant. And it's the box that you take an X value, you take a Y value, you take a Z value, and that point right there is touching, it's inscribed, so it's touching the ellipsoid, all right? If I do that box, if I were to move that box backwards into the second octant, wouldn't it also touch that back edge? And if I move it to the third, it would touch the other edge, and then, so moving that into all the different octants would give me the full box, right? I mean, the full thing I'm looking for. But what's nice about looking at it this way is, what's the volume of this box? If this is X, and this is Y, and this is Z, then the volume is just X times Y times Z, isn't it? And how many of those boxes would make up the entire shape that we're talking about? 8 of them, right? 1 for each octant. So do you agree right now that the volume of that thing we're looking for is 8X, Y, Z from our picture? Yes? Now, the only thing that we really know how to do right now is to find the maximum and minimum values of a function of 2 variables, right? F of x, y. That's what we've spent our time on the last few, today in last class. So I want to try and see if I can get this volume function in terms of 2 variables only. Now, it doesn't have to be x and it doesn't have to be y. It could be y and z. It could be x and z, or x and y. No matter what, I need 2 variables instead of 3, right? Because right now I need to know 3, all 3. So I'm going to try for x and y. How can I rewrite this volume where I don't have a z in it anymore? I mean, right now, are the x, y, and z that you pick, are they free to be anything you want? There has to be some restriction. What's the restriction? That it has to lie on the ellipsoid, right? The x, y, z, that point has to lie on the ellipsoid, which means it must satisfy the equation of the ellipsoid, yes? And the equation of the ellipsoid was here, which means you could solve this for z, couldn't you? And if you solve this for z, you would have z in terms of x and y. Then you could take that and substitute that back into that volume equation for z, which I'm going to do. It's going to suck, but that's what I'm going to do. So let me, down here, write down that equation. I don't have it written down. 9x squared, 36, 4, 36. 9x squared. Wait, hold on. I think I already messed it up. It's 36, 4, 36. 36. Okay, I'm going to come back up to volume, but right now I'm using that restriction and solving it for z. So moving some stuff around. I'm going to divide through by 4 before I take the square root. And now I'll take the square root. So z is 9 square root of 9 minus 9/4 x squared minus 9y squared. Do you feel like factoring a 9 out and then pulling it as a 3? I don't care. It doesn't really change a whole lot. Just leave it in? Okay. All right, now back to our volume. Our volume is now 8x, damn it, x, y, but z now is square root of 9 minus 9/4 x squared minus 9y squared. Is your volume now a function of a single variable, or two variables? Yes? In terms of x and y? So this volume, I think I'll scrap that. I'll put v of xy. Do you have some domain restrictions? What kind? What's that? Yeah, that can't be negative. Are your x and y restricted on a closed bounded? Is your x and y restricted to a closed bounded region? Think about it. Our x and y can't just be anything, right? But they both would have to be positive. Do we agree with that? You would have to have x must be greater than 0 and y must be greater than 0. Why is that? Because of the way that we came up with the drawing. The way we came up with this drawing, I said, okay, this green box is we take an x, a y, and a z, and we're in the first octant. If we're in the first octant, the x and the y have to both be positive, right? Your x has to be positive, your y has to be positive. Yes? And actually, z must be positive also. Yes. That's where the 8 xyz came from. Xyz is the volume of that green box, but there's 8 of them. This was the original picture. Was that whole rectangular box? I'm looking at just the part of that box in the first octant. That's xyz. That's 8 xyz. For a box. Yeah, I mean it would. Yeah, this situation only it would be that way. Yeah, depends on the geometry of what you're faced with there. Rectangular box. Yeah, it would be 8. Okay. Can we say closed bounded though? Yeah, you can't let x be like a million, right? I mean, there is some restriction on x. You can't go past the edge of the ellipsoid, can you? And your y the same thing. Now, even though that is the case, let's just stick with what we have so far, what we know about if we did have a function and we didn't have a closed bounded domain. Let's try and find local max and local min for this. Let's just try and figure it out by computing D and see where we go. No matter what, we're going to need the first partial, right? First partial, that's going to suck. But thus is life. Sometimes it sucks. So I need first partial. So I'm going to have to apply the product rule, right? Right there. So the derivative of 8xy with respect to x is 8y times the square root of all that junk. I'm just going to call it j for junk. And then the derivative of the junk. Well, the derivative of the square root of something is 1 over 2 times the square root of that junk, right? Times chain rule says derivative of what's inside the junk. What's the derivative of what's inside this junk with respect to x? Is what? That's a 9. So negative 9 halves x? Okay. Negative 9 halves x. And then finish off the chain or the product rule. What goes in front of it or next to that? 8xy. Whew, okay. Cleaning this up a little bit. 8y square root of the junk minus crap. Okay, 4, 2, so what is that, 18? X squared y over square root of the junk. Do y'all agree? I shall return to that in a moment. Let's now do the partial with respect to y. The partial with respect to y isn't much better, is it? 8x square root junk plus 1 over 2 square root junk. But what's the derivative of the junk this time? Minus 18y, then times your 8xy. Cleaning that up, 8x square root junk. What do we have here? 9, negative 72 xy squared over square root junk. Someone confirm that. Does that look right? For those of y'all paying attention, hanging around? Oh, yeah, that's fine. That's a pretty standard math thing to do. As long as you just remember it, you got to go back at some point. Yeah. I say standard. All the math people I know, they always would do that at some point. Just say, like, that's too much to have to write over and over and over and over. All right, so here we go. I need to take that and continue to work on it. I need to set each of those equal to 0, don't I? Yeah. I'm going to lasso this stuff and take it to the next page. I say I need to set this equal to 0. Well, that's what you would have to do, right? Some point on a problem. All right, here we go. So let's work on this first one. I want to take that first partial and set it equal to 0. So Vx equal to 0 would mean, well, if I set this to 0, why don't I get a common denominator? Is that all right with you? Or, yeah? So I did multiply top and bottom here by root j. On the top, I'd get 8y times j. On the bottom, I'd have the root. Okay, so I have 8y times just j. And now I'm actually going to write what j is. The junk was, along to 9 minus 9/4 x squared minus, was it 9? Y squared? Okay. And then we have minus, right here, minus, and then 18x squared y squared, or x squared y, all over the root junk equals 0. Now, the good news is I can multiply both sides by root junk now, and it's gone. So I just need to figure out when that numerator is 0. Because I got a common denominator here, put these two together. So I multiplied root junk on top, bottom here. And then when I put them together, they both have root junk on the bottom still. Let's distribute through here. What do we have? 72y minus 18x squared minus 72y squared plus 18x squared y equals 0. Is it cubed? Oh, yeah, thank you. Hold on, I missed that. X squared y right there. I missed a y there and a y cubed there. We agree with this? Man, I sure wish one of those was plus and the other one was minus. Right? But it's not. All right, let me try, still working with this. Take a y out. Okay, I'll take a y out. It's fine with me. That leaves me with 72 minus, or you know what? Let me do it this way. I'll do a negative y out. That'll leave me with 72y squared. I pulled, no? Okay, look, I'll stick with y. Never mind. I'll just stick with y. I don't want to confuse people. All right, minus 18x squared minus 72y squared minus 18x squared equals 0. Now, I can throw this one away, can't I? Throw that. I don't even care. Because y equals 0 wouldn't be a solution. Because remember, we said that the y had to be greater than 0? So that's not, I don't even have to concern myself with that, right? This because y must be greater than 0. Did we say that earlier? Yeah, we said it here. It wouldn't make sense to have y was 0. Then your volume would be 0, right? Okay. All right. Let me try and put those two terms together. 72 minus 72y squared minus 36x squared. Yes? Equals 0. Pardon? All right. This is a single equation. We have two variables in it, right? Let's just hang on to that. Let's go look at the other one real quick. Maybe we can get some information from the other one. On this one, same thing. We multiply top and bottom by root junk. We get 8x times 9 minus 9/4 x squared minus 9y squared minus 72xy squared all over root junk equals 0. That's what's happening when I take the Vy and set it equal to 0. For the same reason, I can get rid of the root junk on both sides. I distribute the 8x through. So 72x minus 18x squared, or x cubed, and then minus 72xy squared minus 72xy squared equals 0. What can I factor out of this? An x, and actually, we could have taken a 9 out also of this one, or 18. Let's stick with this one. I'm getting ahead of myself here. These two are the same, right? So I can put those together. How many times does 18 go into 72? 4. So we have 4 minus x cubed minus 8 xy squared equals 0. And I will toss this one again, because that can't be 0. X can't be 0. And we pulled the x out of that other one, right? X squared, there. Oh, man. All right. Back up here. What could we pull out of this? 18? 9? 36. So 36, 2 minus 2y squared minus x squared equals 0. Get rid of the 36. So that's what we have. We have this equation, and then we have this one right here. Are we all on the same page? We all okay with this? All right, let me go to a new page. We have 2 minus 2y squared minus x squared equals 0. And 4 minus x squared minus 8. 4 minus x squared minus 8y squared equals 0. All right, what can we do here? Set them equal to each other. So if we set them equal to each other, get 2 minus 2y squared minus x squared equals 4 minus x squared minus 8y squared. And adding x squared to both sides gets you that. And let's bring all of our numbers to one side. There's a 2. And bring the y squareds to the other side. That's what, 6 of them? Divide through by 6. Take the square root. Y is positive square root of 1/3. I don't worry about the negative because remember, y had to be positive. So it looks like y is square root of 1/3 is where we have a critical point, right? If that's, I guess at this point we have to kind of say to ourselves, is this where the maximum is going to be? What's wrong? Yeah. You lost? Well, what part? You gotta tell me. Okay. So you have an ellipsoid, right? Think about it geometrically. I mean, because really what we're supposed to do now is figure out what the x would be, right? And then we're supposed to calculate d, which means we need second partials, right? And I don't want to do second partial, do you? No. But let's think about it logically here. If you have this, right, you have different scenarios of what could happen. Now I'm actually dragging my x. I'm changing my x right now. Notice how the volume is changing. We have some optimum solution. If I let x get too small, the volume starts to get smaller, right? If I let x get too big, again, the volume starts to get small again. There's some optimum place to put x so that you get the most volume. And there should only be one, right? There's only one way we can do this. So whatever critical point we find, it should represent that maximum by just pure logic of it. There shouldn't be 4 different places where we get the maximum volume. It should only be one. So we don't have to do any more work to actually convince ourselves that this is going to be our maximum. We just need to figure out what x is, and we're pretty much there. We figure out what x is, then we can figure out what z is, and then we're done. So let's figure out what the x would be. So where do we go to figure out what x would be? The ellipsoid has both x and z in it, though. How about one of these? That's an equation that has x and y in it. If I just replace y here with this, so square this, put this in there, that's what, 1/3, and just figure that out, and you figure out what x would be. So using this, we get 2 minus, plugging in root here, we get negative 2/3, and then I'll say equals x squared. Take the negative x squared, add it to both sides. What's 2 minus 2/3? 4/3 equals x squared. Now take the square root on both sides, and x is 2 over root 3. Again, we're only looking at the positive case because we're in the first octant. Now that you know what x is, you can get z. So get z by now going to that. We had solved for z a long time ago, didn't we? There it is right there. That's with z right there. So plug in 2 over root 3 here, and you would get what? 2 over root 3 would be 4 over 3 cancels, so that's just a 3 here. 9 minus 3 is 6. Plug in 1 over square root of 3 and square it. This should be minus 3. 9. Well, no, wait. It was 6. It was root 3. Root 3. Can you all get Z, you think? Should be 3 here and 3 here again. 9 minus 3, it's 3. So root 3, okay? So I'm not going to show that work, but this would mean that Z is square root of 3, which brings us, those are the dimensions of our box, right? The X is 2 over root 3. The Y is 1 over root 3. And the Z is root 3. That's the dimensions of that one box, right? Inside that one octant. So what are the dimensions of the overall box? Careful. This is the first box. Ooh, bad picture. That first box, it was only in the first octant, was X, right, Y, and then Z was the height, something like that, or I got these backwards. X, Y, and Z. So the full box would come this way, like this. Go back, wouldn't it? There's 8 of them, so here's the 4 on top, then you have the 4 on the bottom. So how wide is it? How wide is it? Well, in the X direction, how wide is it? 2X. In the Y direction, 2 Ys, and then Z direction, 2 Zs, right? So just double each of those, and that's the dimension of the box we're looking at. We still haven't said what the volume is, but I can tell you this is 4 root 3, 2 root 3, and or 2 over root 3, and then 2 root 3. Those should be the overall dimensions of the box with the most volume. The volume you could have gotten by just coming up to that volume formula right there, 8 times X times Y times Z. Right? That 8 there is actually the 2, 2, 2. That's all that is. So what would we get if we multiply all those together? We may as well get a final answer. So the volume is 4 root 3 times 2 root 3 times 2 over root 3 times those cancel. What do we have there? 16 over root 3. Can someone do that on a calculator? Holy crap, I can't believe class is almost over. What? 9.23? 237, something like that. Okay. Why are we what? Well, I have 2 ways of doing the volume. I could do 8 times X times Y times Z, right? And I know, or I can just say, I already doubled each side here. So just, what's that? Why did I do 4? No. This is doubling X, doubling Y, and doubling Z. That's it already. So now I'm just, hey, if I give you a box and I say find its volume and I gave you length, width, and height, you just multiply those 3 sides together, right? That's what I'm doing, those 3 sides together. That's the same exact thing as what we would have gotten had we done 8, X, Y, Z. Because we would have had 8 times 2 over root 3, then Y was 1 over root 3, and Z was just root 3. That gives us the same exact answer. Because 2 cubed is 8, yes. That's what I was just saying, that the 8 is the doubling of all 3 dimensions, 2 cubed. All right, so that 9.237, when I came back over here, remember I was moving this around, trying to figure out 9.23, somewhere around in there. If I try and go in each direction a little bit more, it gets smaller. So somewhere in there, you can see is where it's happening. So not only do we know what the maximum volume that we could get is, we also know exactly the dimensions of the box that give us that. All right. 10 minutes left. don't think there's a whole lot more we can do. 11.7. So you should now be able to handle 23 through 27. Odds. Feel free to do the evens there, 23 through 27. Yes, it was. Because remember last class I said do this, but don't do these. Now you can do these. Now number 37, I'll read 37 to you. 37 says, find the maximum volume of a rectangular box that is inscribed in a sphere of radius r. That's exactly the problem we just did, except instead of an ellipsoid, it's a sphere. And instead of telling you the exact equation of the sphere, they just give you an arbitrary sphere of radius r. So, but the setup is still all the same, pretty much. Well, we have a test a week from today, and we're supposed to cover Lagrange, chapter 11, section 8. Lagrange it's a lot. A lot of times Lagrange gets pushed into the next test. So let's plan to start Lagrange next time, and it'll probably appear on the test as like a bonus or something like that. Because we'll need more time with Lagrange than just one day. Is that what? What, Lagrange? Yes. Yeah. So what should you start doing to prepare for the midterm? So the midterm is such a huge part of your grade. Review your homework, right? Your homework is the biggest thing for you to review. After you've done your homework, I would look at the chapter reviews and try and find problems in the chapter review that are similar to the problems from your homework. Because when I go to make this test, I'm going to go straight to the book. I'm going to start looking at what I assigned for homework. I'm going to start creating problems based on that. It's a lot to look at, but that's your review. I mean, I'm not going to give you like, hey, here's 10 problems, study these. The midterm's supposed to be a test over everything we've done up to this point. You prepare for it. Yes? I don't know. Let me think about it for a second. 1 hour, 40 minutes. You meant like how many problems? Yeah. I don't know. That's the biggest challenge, is to make a test you can complete in 1 hour, 40 minutes. You know, for the final, you have like 3 hours, 3.5 hours, so it's a longer test. For this one, it's not. Yeah. What do you think's fair? What do you think? No card, like a stamp size note card. Well, I've had this conversation with some other faculty, and there seems to be this big pushback from faculty about, don't, if you give your students a note card and I don't, then that's not fair to my students and all this stuff. And well, my opinion is that, the real world, you're very seldom in a room, right? Locked in a room for 1 hour, 40 minutes, and you don't have any access to any information, right? Yeah, I mean, there's so many resources that you have in the real world that if you ever were in a real industry job, you would not be trapped alone, You at least have colleagues that you could bounce ideas off of and stuff. So, but that's why I do like cheat sheets, because it helps you become resourceful, like using your own knowledge and putting it down on a piece of paper. Knowing what you need is part of learning, I guess. So yeah, I think it's fair. Let's say a sheet one regular sheet of paper, front and back, no worked out problems, just steps, procedures, formulas. I mean, the D, obviously, right? I mean, if you want to put on, like cross product, all that stuff, how to find, angle if you're given to, put all that stuff's fine. Just don't work out problems. Sound fair? Okay. One sheet. All right. Front and back. 8.5 by 11. Yeah. Well, yeah. 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 All right. Well, I guess that's it. We're out of time. So everyone have a good rest of your day.